Hey, how you doing? Today we're going to continue the discussion on quantum nonlinear optics by solving for the third order nonlinear polarization and susceptibility quantum mechanically. And from previous videos we've seen that this is the quantity we're interested in mainly because this is the third order perturbed dipole expectation value, and to get the polarization we just multiplied the number of dipoles divided by the volume, and then multiply by this to get the third order polarization. So it's the sum of these four terms, and we have all these bra and kets from previous videos. So we've done the 0th, first, and second order polarizations, and now we will work on getting the third. So I'll start here with the third. Okay, so this is what the third order perturbed wave function looks like. Just a sum over all the perturbed probability amplitudes times the phase factor times the basis state. So all I did from this step to this step was in square brackets here. This is C sub C superscript third. Initially I forgot the sum over C, so that's what this is here. Okay, and also I sort of skipped a step here where I wrote e to the I naught times e to the minus I omega sub I times t as e sub I, because that's just the whole electric field spatial and temporal dependence. Okay, and now we'll just do the bra side by taking the complex conjugate of C sub C and, well, this exponential factor, positive will be there, and this will change into a bra. Okay, so now we have the bra and the ket of psi 3. So we will go ahead and write out each of these terms. I'll call, this will be term 1, term 2, term 3, term 4. So, starting with the first term, which is going to be so let's do that first. Sorry, I realized I made a mistake here. This is psi 1. Okay, so I plugged in these square brackets the bra of psi 2, and these other square brackets psi 1, and these are just dummy indices. So for the expression for psi 1, I did have an a here and an I here, but I changed those because they're just dummy indices. And this e to the negative I omega gt cancels with this e to the I omega gt. And I also changed the minuses to a plus here because we can do that. We're summing over positive and negative frequencies. Okay, that's the first term. Let's move on to the second term. Okay, that's the second term. Very similar to the first. Now we'll move on to the third term. Okay, that's the third term. And I mean, all I'm doing is following the rules that I discussed in previous videos. So if we have a bra psi g here, then we have the dipole operator, and we have the ket psi c that I'm writing as mu sub gc. Okay, and finally we do the fourth term. Okay, so that's our fourth term. Now we go ahead and write D3 as the sum of all those four terms, and you'll see why I changed some positives, some minuses to positives, and I'm also going to try to organize it to make it look as nice as possible. Okay, so sorry about that. For the third term, I started writing the fourth term, so that's why I erased it all and went back. And now, you can already notice a few things. You notice that in the fourth term, all the subscripts on the mu's, they're just reversed. And all the electric fields have the complex conjugate. And that is why I changed the minuses to pluses. So it's almost a complete complex conjugate thing of the third term. I wanted to leave this as a minus, actually. Okay, and now all I'm going to do is just reorder the mu's just to make them I'm going to order them so that the second index on the subscript matches the first index on the next term. So, for instance, in this term, I'm going to swap this with this because I want the b's to be next to each other, and this with that because I want the c's next to each other. And again, I want to write it like that because it makes interpreting the Feynman diagram or the energy level diagram a little bit easier. Okay, so that's our final form of the third order expectation value for the dipole moment. And I wrote it like this to sort of just show you how these mu's are ordered. And I mean, you just take every combination that you can and organize them that way. Because all those processes are occurring in the third order polarization. Those processes being things such as stimulated Raman, coherent anti-Stokes Raman, and all the other 48, I think, Chi3 processes. So they're all captured by this. And again, as with the second order polarization, I'm not going into things. So there's actually 48 terms. I think that's right, like I said. And you don't see those other terms because things such as the intrinsic permutation symmetry, the reality of the fields, those, I forgot what the names of the other things, but I'm not getting into that, so that's why we don't see all those other terms. But, I mean, I wrote these 4 terms, sort of assuming some things, but I could have rearranged some things and got another 4 terms. But those are all accounted for through intrinsic permutation and things of that sort. Okay, so like I said in the beginning of the video, this is basically the third order polarization, but all we do is multiply the number density, and also we have to multiply the constant, the vacuum permittivity, and then we just multiply what we just found. And as for the susceptibility components, we're going to use the relation that the polarization in, say, the x direction is equal to epsilon naught times the sum over all basis states ABC times the sum over all frequencies ijk, and then the susceptibility element xijk. because it's in the x direction. And then you have the electric fields tacked on the end here. So if you want your third order susceptibility elements, this is how you would get it. You just compare that to that. Okay, well, I hope that was helpful. Thanks for watching. Have a great day.